Okay, people, well, I think we might as well start. It truly is a pleasure to introduce Yann Le Cun. I've known Yann for a long time, and when Yann first came to NYU, we understood that we had things in common, and we started some conversations that went across all departments, and that set of conversations ended up becoming the Center for Data Science, which Yann founded, I don't remember when.
2011,
something like that. Yeah. And so the Center for Data Science here really was established grassroots, like ground up, from things that were actually going on at the university, and has been a very successful entity thereafter. There are several people in my life who didn't win the Nobel Prize, and Yann is one of those people. Yann is arbitrarily close to the people who did win the Nobel Prize a few years ago for machine learning things. And a lot of people around here were like, wait, is that physics? And I think it very much is physics. I think a lot of the underlying things in machine learning really are physics things, and it's mathematical physics. It's not kind of machine learning is almost a branch of mathematical physics, and many machine learning practitioners consider themselves to be physicists.
Not me.
Just wondering. Yann, of course, has been showered with prizes. He's very important. In particular, he won the Turing Award in 2018 with Bengio and Hinton. When he was a graduate student, he reinvented the chain rule of calculus. I think Leibniz has priority, but you did okay. That's backpropagation, and one of the reasons backpropagation was important is once backpropagation was understood, then very large models could be trained, and that was the beginning of deep learning. Yann was also one of the pioneers in convolutional neural networks, which is one of the first attempts to bring some kind of symmetry or ideas of symmetries into machine learning, and as people know, that's very close to my heart. One of the main things I've learned from Yann is that intelligence is a very complicated thing, and Yann has always been a critic of the idea that if you can generate good text, you're intelligent. Intelligence is much, much more than text. And in fact, one thing that Yann said to me years ago, you might not even remember saying this, is that birds of prey show certain kinds of intelligence that are unmatched by any creatures in the world. There's certain kinds of intelligence that are unmatched even by humans. And there's no reason for us to think of ourselves as uniquely intelligent because we move words around. So I think that's been a very important thing. Yann, shortly after we established Center for Data Science, Yann went to Facebook, where he handled a budget that I think has either 11 or 12 decimal places. Recently, that whole situation has been in the news. In fact, Yann was in the New York Times today. There's a picture of him and some discussion of the shakeup at Facebook, and I believe that Yann has moved on to new things.
Soon, in 3 weeks.
In 3 weeks. He's on his way towards new things. Anyway, I asked him to say things that would be at least somewhat provocative.
Thank you. I don't know how to say things that are not provocative. Okay, I have to say a few words about my connection with physics. Okay, I'm not a physicist. I'm not a computer scientist either, by the way. I studied electrical engineering as an undergrad, and it was France, so I had to take a lot of physics and math. And then when I started getting interested in neural nets, it was because of a connection with physicists. So I was hanging out with a lot of physicists, and I learned everything about statistical physics and free energy and variational methods and all kinds of stuff, and Hopfield nets, Boltzmann machines, all that kind of stuff. I have one paper in physical review letters. Does that count?
Yes.
Okay. With math that I don't understand.
Okay, then less.
It's like replica symmetry breaking stuff that I have no idea how it works, but it was a cool result that came out of it. Okay, and my other connection with physics is that I took that picture. I took that picture in my backyard in New Jersey, so terrible skies. But I used narrowband filters, H alpha, sulfur, oxygen. And that's M51, and it's got ionized hydrogen regions here that are star creation regions. I have a new telescope that I haven't figured out how to use yet. That's 17-inch. I'm looking forward to playing with that. So that's one of my hobbies. Okay, so I'm going to talk about world models, and it's something that maybe is relevant to physics, but also very much to the future of AI. So a lot of people have been interested in sort of getting AI systems to the level of human intelligence, and we can question whether that's a good idea to sort of make AI systems that have the same level of intelligence as humans. But I think it is, because intelligence is really kind of the commodity that we need the most. In academia, obviously, we already have it. In government, though, not so much. And so it'd be nice to, sort of have computers or machines that assist us and make us smarter. And that means building systems that have the similar type of intelligence as humans, because we want to be able to interact with them, right? So a good sci-fi movie, if you want to look at this, that's 12 years old, is Her. It's like the story of interactions of a sort of lonely dude with AI assistant. But we need machines with human level intelligence because we are used to interacting with other humans. So that would be kind of the best way for them to assist us. Okay, but we despite what you might hear from some of my more adventurous colleagues in Silicon Valley, we're nowhere near that point. Like we don't have even the basic principles to reach anywhere close to human intelligence. Basically, current AI and machine learning really sucks when we compare it to humans and animals. Humans and animals have mental models of the world that allows us to have intuitions and predict what's going to happen and plan actions. Our behavior is driven by objectives, which is not the case for things like large language models. And we can reason and plan complex action sequences, and again, large language models don't do this. So large language models have limitations in the sense that they don't understand the physical world. Oops, wrong button. So I don't like the phrase AGI, artificial general intelligence, because that phrase is designed to designate human level intelligence, and it has the hidden assumption that human intelligence is general. And I'm sorry to say, human intelligence is absolutely not general. We're very specialized. This is the point you were just making. Some animals are much better than we are at certain intellectual tasks. And so we're very specialized. And so the whole phrase AGI makes absolutely no sense. However, artificial superintelligence makes sense. It would be intelligent machine that is as intelligent as humans in all the domains where humans are good. And of course, we already have machines that are much smarter than humans in some narrow domains. The question is, can we have a machine that is, as intelligent as humans in all the domains? And for that, so I call this advanced machine intelligence, AMI. And in fact, I'm leaving Meta and starting a research-focused company, and the name of the company is Advanced Machine Intelligence. And by the way, this is confidential data. The war between friends, right? So we need systems that really learn how the world works through sensory inputs, like humans and animals. Vision, touch, everything else. Systems that have persistent memory. So in mammals, there's a special piece in your brain called the hippocampus, which is basically used as short-term memory, working memory. Systems that can plan complex actions so as to fulfill a particular objective, accomplish a task. Systems that can reason, inventing new solutions to unseen problems, which LLMs are completely incapable of doing. And systems are controllable and safe by design, not by fine-tuning, which is also the case for LLMs. And so we might ask ourselves, how is it that, how do humans and animals learn to apprehend the world? And this is a chart that was put together by my colleague Emmanuel Dupoux, who is a developmental psychologist, a cognitive scientist. And he says, at what age do babies, infants, learn basic concepts like object permanence, the fact that when an object is hidden behind another one, it still exists, right? So that pops up around the age of 2 to 4 months. The distinction between inanimate objects and animate objects, babies can spontaneously learn that around the age of 3 months. babies develop like an intuitive sense for categories, like they know that the table and the chair are different and the dog and the cat have different things. They don't need to know the name of things, right? They know there are different categories. So that pops up around the age of 4 to 5 months. And then things like intuitive physics, okay, like gravity, inertia, conservation of momentum, that pops up around 9 months. So if you put a 6-month-old baby in front of the scenario where there's a little car on the platform and you push it off the platform, it appears to float in the air. 6-month-old baby would barely pay attention. A 10-month-old baby will go like this. And this is how psychologists actually know that the internal mental model of the world of the baby was just violated. You just pay attention. Okay? You need to pay attention when your model of the world is being violated because it could kill you, right? But you need to adjust your model, right? So you measure the degree of surprise of babies and the amount of time they stare at a situation to figure out if something violates their model. If you put an 8-month-old baby on a high chair and you put a bunch of toys on a high chair, they will systematically take the toys and throw them on the floor. They're doing the experiment to verify that gravity applies to everything. Okay, that's the baby physicist. There's actually a book with that title. Yeah.
Do we know whether baby is actually learning or like it's just the brain is developing as they grow up?
No, it is learned, and you can learn different physics depending on like. There's a lot of video games that have like weird physics, and you adapt to it like super quickly. And so obviously you weren't born with that hardwired in your brain. You're not even born with the concept that the world is 3-dimensional, for example. But obviously the fact that every point in the world has a distance from you is the best way to explain how your view of the world changes when you translate. It's just the simplest explanation, right? So a lot of learning is based on like developing theories that explain what you observe, and you can think of intelligence as developing itself by training itself to predict, right? If you predict what is the world going to look like when I move my head to the left by 40 centimeters, and I can do a good job at predicting this, that means I have some representations of the 3-dimensional nature of my environment. If I can predict the trajectory of objects that I throw in the air, I have some good representation of what gravity is and things like that. So training yourself to predict is a good way of kind of developing theories. Okay, they're not equations; they are like theories in your brain of how the world behaves. So how do we get machines to do this? And people are fooled by recent progress. Like they see large language models and they see large language models, passing the bar exam, solving integrals, winning international math Olympiads, doing all kinds of, composing poetry, summarizing long documents and being able to explain to you what the essential things are in it. Most of this is retrieval. Okay, so it's like the students in your class that are, not so great, but they can learn the formula by heart, right? So they regurgitate them. But that's not the same as really sort of having a deep understanding of the underlying physics. So it turns out that language is simple, relatively speaking, compared to the real world. And understanding the real world is still out of reach, mostly, of AI systems. So we don't have AI systems that are nearly as smart as a house cat or a dog, let alone a dog. A cat has 860 million neurons. It's about 100 times less than humans. It's about 86 billion for humans. The dog has about 2 billion neurons. So yeah, dogs are way smarter than cats. And current robot intelligence doesn't come anywhere close to this. A house cat can plan very highly complex actions. There's tons of videos on YouTube of cats doing incredible stuff. Right? A 10-year-old or even a 6-year-old can clear up the dinner table, fill up the dishwasher without learning. You just ask them to do it the first time, and they'll do it mostly without breaking anything.
Experimented false. But
There are exceptions. The tricky part is to actually convince them to do it. That's and 17-year-olds can most of them can learn to drive a car in about 20 hours of practice. We have millions of hours of training data of people driving cars, recorded by Tesla and various other players. So we could train in principle a neural net to imitate humans by imitation learning. And it still doesn't work. It's not nearly reliable enough to have completely autonomous level 5 self-driving car. Okay? So how is it that a human can learn to do this in 20 hours of practice, and we have millions of hours of supervised training data, and we still can't use AI systems that do this? The real world is just hard. And this is an example of what's called the Moravec paradox. Hans Moravec was is a roboticist, and in 1988 said, how is it that the things that are completely trivial for humans to do, like navigating in this room or picking up an object, things like that, we don't even consider them intelligent. But they're impossible to do for computers, whereas like playing chess and things that we think of like the epitome of human intelligence, actually it's relatively easy for computers. In fact, humans totally suck at chess. Like we're terrible at chess. We're terrible at Go, and all of those games that computers, it turns out, are much better than we are at this. So another example of human intelligence not being general, and perhaps it's due to this very simple fact. Let's take a big LLM from, let's say, a year ago, like Llama 3 or something from the colleagues at Meta. It's typically trained on 30 trillion tokens. Okay, you collect all the words available freely on the internet, and you decompose those words into tokens, which are like subword units. And typically, the entire text publicly available on the internet, breaks down to about 30 trillion tokens, 3 10 to the 13. Each token is 3 bytes, so the data volume is roughly 10 to the 14 bytes. Okay, it's a big chunk of the knowledge, human knowledge, that has been turned into text. Unfortunately, that's not nearly anywhere close to the total corpus of human knowledge, because most of it has nothing to do with language. So take a human child. Human child in the first 4 years has been awake a total of about 16,000 hours, which, by the way, is the tiny amount of video. That's 30 minutes of YouTube uploads. We have 2 million optical nerve fibers carrying visual information from the retina to the visual cortex in the back of the brain. We have 1 million fiber per optic nerve fibers, and each of them carries about 1 byte per second, roughly. So it's about 2 megabytes per second getting to our brain when our eyes are open. And do the arithmetics, and you get about 10 to the 14 bytes. So in 16,000 hours, which is 4 years of a child, you get the same amount of data as in all the text available on the internet, which would take about 500,000 years to read. It would be kind of boring too.
Did you get the 1 byte per second from the average firing rate?
The estimates vary from 0.3 bytes per second to about 1 byte per
Because
second.
the retina is a cascade every 2 photons. Every 2 photons, the retina is a cascade.
Yep.
Generates a cascade
The
of
retina, yes, but not the
Yeah.
optic nerve, because you have 60 million
but the retina is
photosensors.
involved in visual processing.
Sure, but
It's
it
not
gets
the same.
compressed like crazy,
Yeah.
right? Because you have 60 million photosensors, and it gets crunched down. Your retina has 4 layers of neurons in front of it that basically compress information so that it fits on 1 million optic nerve fibers. Because we're in a local minimum of evolution, like all the vertebrates have this bug, which is that the wires of the photosensors come out the front, not the back. And so you have neurons in front of your retina, you see through them. And then they do some processing to compress the signal onto a small amount of optic nerve fibers. If it wasn't compressed, you wouldn't be able to turn your eyes because you would have gigantic optic nerve fibers. And also, that's a blind spot. That's where the optical nerves that are punched through your retina.
But Stefano's point is valid here that you're comparing a raw data rate to a very cleverly compressed data rate. So it's,
Sure.
I think the factor is much larger if you take a step
But
notes.
to some extent, language is already compressed, right? I mean, it's a communication
Mhm.
medium, and it has to be compressed and noise robust to noise, right? And so it has to be discrete, blah blah blah.
Yeah,
So I mean,
yeah.
an argument is video is much more redundant than language, but that's precisely what you want because you can't do any learning unless you have redundant data.
I'm just wondering, so like if you think about someone like Helen Keller, who learned obviously pretty much everything an average human would know,
Yeah,
but without all this data,
she had touch.
yes,
You can't survive without touch.
yes. But does this necessarily mean that data volume is somehow a good determining factor?
Okay, so she had a hard time learning all that stuff, and she was never at the level of other humans, but it's pretty impressive that she was able to kind of develop at least some level of understanding of the world, and but it's touch,
She also
and the bandwidth of touch is almost as high as vision. You have pretty much as many touch sensors as you have photo sensors. Yeah, it's kind of impressive. Okay, so it tells you one thing. We're never going to get to human level intelligence by just training on text. We need the real world, we need physics. Okay, a second question is, what is the best way to produce an output? Okay, from a machine learning system or biological systems. Okay, so the standard way to use a neural net is you feed it an input, you run through a bunch of layers in the neural net, and out comes an output, and you just produce that. Now, computationally, there is a lot of problems that you cannot really efficiently reduce to this process. Despite the fact that in theory, neural nets are universal approximators, in practice, there's a lot of computational problems that really you cannot kind of crunch into a reasonable size neural net. Because maybe the computation you're trying to do is intrinsically sequential and you only have 30 layers in your neural net. So a better way to produce an output is something like this. It's called energy-based model. So another connection with physics. So basically you observe the world, you run this through some encoder that produces a representation, abstract representation of the world. And then you have another neural net here that has an implicit output that is not represented in this diagram, a scalar output, which you can interpret as some sort of energy. And what this energy represents is the degree of incompatibility between the input and the output. So you make a proposal for the output, and you ask this system, is this output compatible with my input? Okay, so here's a picture of an elephant. Is this the label for elephant? Is this the word elephant or something? Okay. I mean, if you give the system here elephant, the energy, the scalar output of this function should be small. If you give another label, table, the energy should be higher. Okay? So the inference there is not propagating forward through a bunch of layers in the neural net. It involves propagating forward in a few layers of neural net, but it involves searching for an output that minimizes some energy function. And the big advantage of this is that it's computationally much more powerful intrinsically, but also it allows you to represent dependencies or relationships between the input and the output that are not functions. In other words, there could be multiple outputs that are compatible with this input. And this process of inference by optimization might actually give you all of them if you do it right. So that's really a much more powerful way of doing things. And in fact, this is a very classical way in classical AI, like before machine learning. The way you produce an output is you search, among all the space of all possible configurations of a problem, you search for one that satisfies a particular criterion or minimizes a cost of some kind. And this type of inference really enables zero-shot solving new problems by searching for a solution that you were not trained to produce. Right? This is what research is. This type of inference by optimization is similar to what psychologists call system 2 in human psychology. compared to system 1. Okay, so LLMs are autoregressive predictors. You basically take a sequence of symbols, you feed them to a big neural net, and you train this neural net to predict the next symbol. It's a discrete symbol. There's only a finite number of those, so it's basically a classification problem. Can I produce the best score for the symbol that is actually observed in a large corpus of text? And once the system is trained to use it, the system actually produces not a single token, but a probability distribution of all possible words or tokens, of which typically there is about 100,000 possible, right? So it gives you a big vector of probabilities, and then you sample from that probability distribution for a definite thing. And once you sample, you shift that sample into the input, and now you can predict the next token. And you keep doing this, shifting the predicted output into the input and then predicting the next. That's autoregressive prediction. This is the way LLMs work. So there's no inference by optimization or anything like this. The only way you can do it would be to generate multiple sequences of tokens by sampling multiple samples from that distribution. So you get this kind of big tree of sequences of symbols, and then have another neural net rate which ones are the best, and then pick the best ones. That's what they call reasoning, okay, which really is an abuse of language. Okay, there's an issue with this, which is that if you imagine that there is some probability E for a token, whenever you produce a token, there's a certain probability for it to take you outside of the tree of reasonable answers, correct answers. And you assume the errors are independent, which of course they're not. Then as you produce more and more token, the probability that your sequence of tokens will be correct decreases like, e minus e to the power n is exponential decay. Now, of course, those assumptions are wrong, but the result is actually true. The fact that the longer you ask the system to, produce a sequence, the more likely it is to be garbage. And there's some theoretical papers on this. Can I ask a question? Yes.
It seems like that hypothesis is pretty easy to test. You could take an LLM and ask it to produce text of some length and then double the length and so on.
Yeah.
And see if the fraction of reasonable responses as rated by some human reader or something.
That's right. And there are a few papers on this because people have actually tested that. Yeah. And it verifies the fact that you can.
So I mean, this is not like a unique thing to long-term models, right? Like,
A unique thing too?
It's not unique that anything that's one-dimensional can't have long-term and short-term. Like, it's always gonna. And like with technology, every computer chip's gonna break eventually, right? But people fix this if you have error correction. Right?
No, but if you produce a piece of text that is very long and you produce it by searching through all possible text for one that has some properties, you're not going to get this, exponential decay of probability of being correct. You can get something that's globally coherent.
How long can humans stay coherent?
That's a good question.
But I know at least one guy who cannot stay coherent for more than 2 words.
Yeah,
Right?
sure. Well, there is an upper bound at about 120 years for sure. Okay, so what's the solution to all of this? And where I think AI research should go over the next few years, and something I've been working on for about 10 years now, is what's called world models. So what is a world model? World model is given an observation, X, raw data from sensors, whatever they are. Let's say video, but it could be anything. Run that through an encoder, you get an abstract representation of the state of the world. Let's call this SX. And then you wait for a little bit, and then there's a future observation of the system. Let's call this Y. You run this through an encoder. You get a representation of it. Can you train the predictor to predict what the representation of Y is going to be from the representation of X? And the diagram I have here is one that would be used for training such a system, such a world model, right? So you show it X, you show it Y, and you train the encoder and the predictor to minimize the prediction error. Now, if it's an action condition world model, there could be an action that you feed to the predictor that represents what happened between here and here. Okay, so maybe this is a physical system, and what you did is heat it up, or I don't know, put some sauce in your mixture of chemicals, or whatever, right? Or twist your 2 layers of graphene, right? By 1.38 degrees or whatever is the magic angle for it to become superconductor. And that would be, if we had a way of training a system like this, that would be great, because we could feed it to any kind of data and it would find an abstract representation space within which to make good prediction, ignoring all the details about the inputs that are not predictable. Okay, this is a very fundamental thing in artificial intelligence, natural intelligence, certainly in science, particularly in physics. The fact that you never model every detail of a system that you observe. You always try to find an abstract representation that allows you to, that preserves the relevant information about the system that allows you to make predictions, right? Ignoring all the details you cannot predict. So let's say you want to, I don't know, you're designing an airplane and you want to do computational fluid dynamics to kind of design the airfoil of your airplane. You can, you cut up the space into little cubes and you represent the state inside of the cube by, velocity, that's pressure and temperature or something like that. And then you solve Navier-Stokes equations. And then from this, you can derive things like, lift and drag and various other things. And angle of attack for stall and whatever you're interested in.
So if your encoder is just identity, then this is just an action conditional generation, right?
Yeah, it's a
Your
generative
predictor
model.
could be a diffusion model. And
So if this encoder does not exist, then it's a generative model that
Yeah.
reproduces all the details about your input.
Right.
Okay, but the example
well, the
I
feature,
was
because the predictor is like a generative model that gives you the next image, right?
the next
Yeah, whatever.
details,
Yeah.
whatever your data is. So if it's video, it would be at the pixel level,
Yeah.
right?
Yeah.
But we never do this in physics, right? Because like if we want to make, in the fluid dynamics example I just cited, at the lower level, you could simulate every molecule of air bumping into each other and onto the airfoil, but nobody ever does this, right? We always abstract away the individual molecules. The same way we can say PV equals nRT and ignore the individual motions of molecule, but still have some predictive model that when I heat up the box full of gas, the pressure will increase. Or if I asked, where is Jupiter going to be 100 years from now? I only need to give in 6 numbers, right? 3 positions, 3 velocities. Like the rest is irrelevant. And we know a lot about Jupiter, right? So this concept that we need to find an abstract representation before we can make prediction is really central to intelligence and science and everything. And the stuff we ignore in the encoder, you call it entropy.
But in physics, the representations we use are not data driven. They're very, very theory driven.
That's right. But then
You're going to
but that
address
works
it
for
feels like you're headed towards, we're going to learn all this from data,
Right.
but we do a lot of learning from data before we get to our theoretical.
So there are systems for which the approach of trying to figure out the elementary equations actually works. There's a lot of situations for which it simply doesn't work, or if it works, it doesn't work in those situations. Like Navier-Stokes would do a good job as long as your flow is laminar, but as soon as you have turbulences, not clear, you get accurate predictions. Or if you have complex dynamics in chemical reactions, or whatever. Right, and or complex systems like a galaxy, or not talking about spin glasses and stuff like that, which are more complicated, but like anything that has some emergent property, or even a physical system that is relevant to engineering. Like take a turbojet engine or turbofan has typically about 1,000 sensors. There is no complete phenomenological model at the moment of the future state that can predict the future state of a jet engine given the previous state and an intervention or an action you're doing on the system. Yeah, if you consider this like a physical system, this could be an intervention, like an experiment you're doing on the system. Can you predict the result?
But that's different from the way we understand the world, right? So, because there are certain things that we very intuitively understand, but things like motion on Jupiter, we build computational theory that do not exist in our head.
Well, it's
right. Mathematics is an extension of our cognitive capabilities.
It's actually exactly the way we understand the world. Okay, you don't need any equations for this, right?
No, I understand. but to make a prediction in the future, to actually give a number, I have to do it mathematically.
Well, correct, but that only.
We knew that Stefano outperforms Yann.
That only works in certain situations where you can actually write down the equations. So there are situations for which the behavior is just too complex. Like even modeling at the physical level, which a lot of people in robotics are trying to do.
Yeah.
You can model like the dynamics of an arm of a robot. You can just write down the equations. You can even model like a humanoid robot walking around and stuff like that. But like as soon as you try to get the robot to interact with an object or grab or do manipulation, simulation stops working. Like it's not nearly accurate enough to really be. So, that's really what we should build. Like, something that runs to produce representations of the world that allows you to make predictions and ignore all the details. Maybe take an example. You can train a system to predict what happens in the video, right? So why would be a video? And then you mask a piece of that video. Basically, that's like a corruption or something. So you only see the beginning of it. And so now that system has to train itself to predict the missing pixels in that video. That's an impossible task. It's completely unsolvable. Like if I take a video of this room and I pan slowly and I stop here and I ask the system, tell me what the rest of the video looks like. Well, I can figure out, there's a bunch of people sitting in chairs, this room is finite, there's probably a wall at some point. There's absolutely no way in hell it can predict what you guys look like, right? It cannot predict the texture of the ground, of the floor, or the wood of the wood panel of the door. So most of what happens in the world is just not predictable. And if you train a system to try to predict what's not predictable, you kill it. I mean, it basically doesn't work very well. And we have a lot of empirical evidence that I've been trying to work on video prediction for over 10 years. And for the first 5 or 6 years, it didn't work at all because we were trying to produce pixels. And we used, all kinds of latent variable models, diffusion, whatever. It just doesn't work that well. In fact, that's an example. Here is the neural net is trying to predict what happens in this video by stopping it at some point, and what you get is blurry prediction. Same here at the top. Why blurry? Because the system doesn't know what's going to happen, so it predicts the average of all the plausible features, and that's a blur. So if you put latent variables in it, in simple cases like videos, stylized videos like this, you can get like crisper predictions by sampling this latent variable, but it's not entirely satisfactory. So instead, what I'm proposing is this architecture that's called JEPA. That means Joint-embedding predictive architecture. And basically, it's a non-generative model in the sense that we're training the system not to predict at the pixel level, but to predict at the representation level. Okay, and that's a key concept. So can you train a system like this? And the answer is, okay, so that's the difference between the generative architecture on the left and one of those joint-embedding predictive architecture on the right. Okay, those are deterministic functions, those kind of funny shaped modules, and this is a cost function. It's basically something that takes variables and produces scalar output. Think of it as an energy, if you want. And to train the system here, it's easy. You just train the parameters of those neural nets to minimize the prediction error. Here it's tricky. The reason it's tricky is that if you just minimize the prediction error, there's a trivial solution where the system basically ignores the input and produces constant representations, and now your prediction is trivial. Okay, and your prediction error is 0 all the time. In fact, this kind of model, they were not called this way, but the concept that the brain is a prediction machine that trains itself to predict, was kind of reduced to a kind of theory by theoretical neuroscientists, and they call this predictive coding. So the way the brain encodes percepts is by training itself to predict. But if you predict at a representation level, a famous neuroscientist, physics background, told a shocked audience, the best way to solve that prediction problem is to shoot yourself in the head. Because then your prediction problem is trivial. So this is called the collapse problem. How do you fix this? How do you prevent the system from just trivially ignoring the input?
But isn't there a question about what you're encoding, right? Because that's the physics that you're trying to predict.
Yeah.
You could encode in different ways, and
You can encode all kinds of different things, and so there should be some bias in your objective function to determine what type of information you want to extract from the input. But basically, the key determination here is I want to extract all the information that I can actually predict and ignore all the stuff that I cannot possibly predict. Right? That would be the most general criterion. Now, of course, we have to bias it in some ways. Like human babies, for example, are hardwired to pay attention to motion. So when something moves, they turn their eyes to that, right? And that kind of biases the distribution on which they train their visual system and their prediction system and their one model. So you can bias it in various ways. But that's basically, this idea that you have to run an abstract representation before making prediction is really fundamental to science and physics and modeling and intelligence and reality.
Is it too much to ask that you should predict everything that's possible to predict?
Yeah.
Because an organism predicts the things that are necessary for its survival and reproduction, presumably, right?
But if you don't know in advance what's going to be necessary for the survival, you end up with humans. Big brain, so that you train your world model to be as general as possible, so that you're adaptive to new environments and not kind of highly specialized for a particular thing. It makes you flexible if you can run a general world model. So, this idea that we learn, in principle, we could describe everything that takes place in this room at the moment in terms of quantum field theory or something, quantum chromodynamics or whatever. That would be completely impractical. We would need to measure the wave function in the universe within maybe a cube, a light year containing this room or something. If you want to take into account entanglement. So nobody does this, right? You can simulate things at that level, but you can only simulate them for a femtoseconds and only a few particles. If you want to make longer term simulations or bigger systems, predictions that are longer term, you need to go to a higher abstraction level, right? And we invent those abstractions, particles, atoms, molecules, okay? And then in the living world, proteins, organelles, cells, organisms, individuals, societies, ecosystems. So we have this whole hierarchy of abstractions. Each level ignores a lot of details on the level below, but still can make predictions and can make longer term predictions that are more accurate in the long term because they ignore all the details that are not predictable. And every level in this hierarchy is a different field of science, right? At the top you have psychology or sociology, and biology, and cell biology, and biochemistry, and blah, 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 right? So, yeah, those models have been around for a while, but essentially, if you have a one model, you can use it to build intelligent systems. And I wrote this paper 4 years ago that I put online on Open Review. It's not on arXiv. This is for people to be able to comment on it. And it's basically where I think AI research will go over the next 10 years, 4 years ago, so the next 6 years. And here is how you build an intelligent system if you have a one model. So you make an observation, you run this to some perception module that extracts an abstract representation of the state of the world, the current state of the world. You might want to combine this with the content of the memory, because right now I can perceive the state of the world in my immediate environment, but I have a much broader idea of the current state of the world outside of this room that I'm not currently perceiving, but maybe have stored in my memory. So combine those two things, feed this to a one model. And what you feed to a one model is a proposed action sequence. So something I could do. And using my mental world model, which basically is my entire prefrontal cortex, can I predict the resulting state of the world that would result from taking these actions, right? If I want to accomplish a particular task, I can feed this predicted state to an objective, think of it as a cost function and an energy function that measures to what extent a particular task has been accomplished or not, right? So it takes the value 0 if the task has been accomplished, and a larger value, the less I accomplish the task, if you want. There might be other cost functions here that implement safety guardrails. I don't know if this is a domestic robot that is cooking. It's got a big knife in its hand, and there is a term here in the guardrail that says, don't flail your arm if you're a big knife in your hands. That could be dangerous. And the process by which the system works is by it searches for a sequence of actions among all possible sequences of actions. This could be optimization in continuous space. It searches for a sequence of actions that minimize the task objective subject to the guardrail constraints. Okay, all of those modules are differentiable, so in principle you can use gradient-based methods to do this planning, and this is planning. In fact, it's if your one model is like a step function that says, you know, state at time t, single action, state at time t plus 1, then you can apply the one model. So this is not like an intelligent system, but it's more like the modeling an experiment in physics or something. The one model is your current model of the phenomenon, and this will be an intervention or experiment that you imagine doing. Can your model predict what the outcome is going to be? Or can you design an intervention that will produce a particular result if you want a particular result out of your experiment? Now, if you have a one model, you can of course feed it a single action. It's going to make a next prediction for the next state, but then you can feed a second action and just apply it autoregressively multiple times to predict the outcome of a sequence of actions. And still using gradient descent, because everything is differentiable, you can figure out optimal action sequence that will fulfill a particular goal. Now, the world is not entirely deterministic, so you might need latent variables, and ultimately you want this whole thing to be hierarchical. I'm not going to go into the details of that, in particular because we don't know how to do this yet. But ultimately we have a whole plan for research and development over the next few years to basically make this work. And we already have results, which I'll show you in a minute. And what I proposed in this vision paper a few years ago is kind of a whole overall architecture that sort of assembles all those modules that might eventually take us to perhaps something similar to cat-level intelligence, dog-level intelligence, perhaps human-level intelligence if we do it right. But it's going to take a while. It's not going to happen next year. So the way you train the system is using this idea of energy-based model. If you have variable x and y, and you want to train the system to capture the dependencies between x and y through this idea of energy-based model, you have an energy function that takes x and y, and the inference process consists in finding the value of y that minimizes this energy. But then training the system consists in, if these are your data points, let's imagine x and y are scalar. If these are your data points, you want your energy landscape, this f function, to take low values on the data points and higher values outside, right? So that whenever an x shows up, you can look for values of y that have low energy and perform inference this way. Okay, so there's, yeah.
How are you sampling once you've trained the energy?
There's no sampling whatsoever. Yeah, how do you train the energy? That's a better question.
And once you've trained it, you then get a ultimate distribution. Or was that not?
Not necessarily. You may not be interested in any distribution whatsoever. You just want to, like if you are, if you're driving a car, if you have an automatic system that drives a car, you don't care for the system to tell you, I need to turn left with probability 0.7 and turn right with probability 0.3, right? You just want it to actually make the right decision. So there's lots of situations where you don't need distributions. So anyway, yeah, how do you train this? That's the big question. So you have two categories of methods to train models like this. So one category, well, there's three categories, one that doesn't work, okay? And that category is what causes collapse. The collapse I was talking about earlier is that you take your data points and you tune the parameters of your energy function so that the energy of the data points goes down. but you don't do anything else. And what can happen is that the energy function ends up being 0 everywhere. And that's not a good model of the dependency between x and y, because you want the energy to be low on the data points, but you want it to be higher outside. So now 2 classes of methods. Contrastive methods. So contrastive methods consist in sampling points outside the manifold of data. Think of them as corrupted versions of your data points, for example, and then push their energy up while you push the energy of the data samples down. Okay? Unfortunately, that doesn't scale very well because in a high-dimensional space, the number of those green flashing points that you need to sample grows exponentially with dimension. And so, not so hot on it. There's another class of methods that I would call regularized, and those you have a term, a regularizing term in your loss function that minimizes, when you minimize it, it tends to minimize the volume of space that can take your energy. That sounds a little mysterious, but you can actually do that. So those are those 2 categories of methods. And let me skip ahead a little bit. Yeah, so if you're interested in probabilistic modeling, you can turn energy functions into probability distribution using a Gibbs distribution. Unfortunately, most of the time you get an intractable partition function, and you have to use rational methods and Monte Carlo and Markov Monte Carlo and blah, blah, blah. So I made a list of standard machine learning and statistical estimation methods as to whether they are contrastive or regularized or architectural. I'm not going to go through the detail. But what's been happening over the last 5-6 years is that people have trained those joint-embedding architectures for learning good representations of images and videos. And the empirical results is that training a system to learn representations of images and videos this way, through joint embedding, works much better than training representations by reconstruction, or prediction. Okay? So those joint embedding architectures for images and video and other noisy high-dimensional continuous data simply work better than any generative approach that attempts to predict every detail. And you can test that. When I say they work better, is that you train the system to learn whatever representation it needs, and once you have the encoder, you stick a simple classifier on top of it that you train supervised, and you measure the performance on some benchmark. There's a bunch of different methods that people have come up with to train those joint embedding architectures. I'm not going to go into the details of this because I'm running out of time, but many of them come from my colleagues at Meta. So things like, BeWare is from Google, Synsiam is from Meta, DINO is from Meta, IJPA from Meta, VJPA from Meta, and there's sort of various ways to kind of make sure those things don't collapse.
So there's no decoder here. So you're living entirely in the.
If you add a decoder, you actually kill it. It works not as well. If you also train it to reconstruct or predict and it pixel out.
Is there a intuitive reason for that? Like using a decoder really would make it that doesn't work.
No, because the system is going to settle on some representation that computes a good average of all the plausible things. Like it's going to be a blurry picture of this carpet or the texture or you guys, and basically the representation is not as good.
Well, and because you put the representation behind some terrible object, your representation probably won't be interpretable in the way that, say, physicists like.
Oh, it's not going to be interpretable, right? I mean, you're going to have to train a head on top of it to do anything with it.
So it works well in an input-output sense, but it might not lead to insights about.
No, I don't care about that.
Yeah, you don't care about that. It's true.
Yeah. So what's happened in the last few months, only 6 months, is that those self-supervised systems trained to represent images have started surpassing in terms of performance every supervised system. And in image recognition is a huge amount of supervised data, like lots and lots of supervised data. And so you would think that supervised learning would, actually still dominate, but no. Like self-supervised pre-training really works better. For images, the same way it's been working better than purely supervised method for language for a number of years. And you can use, let me skip ahead. So this is the latest generic image representation system trained completely self-supervised. What you see here is the curve of performance of self-supervised learning in blue compared to supervised learning in orange and weakly supervised learning in purple. And the conversion factor, blue now is above the others. And it's due to just better training, better data, better methods, blah blah blah. This DINO v3 system is fairly generic. It's probably the best generic image representation system that we have. It's applicable to all kinds of things. Like you could use it to classify galaxies.
What about data efficiency and size of the models that are required, right?
Efficiency, numerical
Data efficiency, like if these were like really how we work, it would require far less data than the alternatives, right?
That's true.
And how does it do?
Data efficiency? It's horrible. I mean, this thing is trained
still
on
horrible. Okay, so
ridiculous amount of data, but we have that data, and it doesn't need to be labeled, so it's cheap.
Yeah.
And it's not like the amount of computation you need to train those models is not really as big as LLMs. The biggest models like this are a few billion parameters. Compared to LLM, they're tiny. They don't need to store a lot of memories.
Yeah, and you have 4 minutes.
Okay. So I'm going to flash a few examples of how you use those techniques to build world models and do planning with them. So this is work here at NYU with a colleague Laurel Pinto and a student we have in common, Xavier Jou. So basically you use the representation produced by DINO v2, which is the previous generation, and then you train a predictive world model with these action conditions in various environments, and then use it for planning. So once you have trained this predictive world model in representation space, you apply it multiple times, something like 5 or 10 times, with hypothesized actions, and by optimization, you figure out the sequence of actions that will minimize the distance between the predicted final state and the target state that you give the system. Let me show you a video of how this works. So this is the initial configuration of a board. And these are target states, and these are the actions that are planned by the system to make the planner look like the target state starting from this random initial condition. And it does this kind of with something called receding horizon planning. So it plans like 5 actions ahead, and then it takes the first action and replans and things like that. And we've applied this to a bunch of different situations with planning, and it works okay. Okay, there's still a lot of progress to be made there, but it's pretty cool. This is a similar work by Anya Barr, who's at Meta, where you train the system with 2 video frames, like this one and that one, and you tell it what the transformation between those 2 frames was. Okay, like by how much the robot kind of translated and rotated. Okay, so basically what the system learns is, here's what the world looks like, here's an action I can take, what is the world going to look like next in representation space? And then you can do this for planning trajectories of a robot by giving it a target view, and it will kind of navigate to that target view. I mean, there's a bunch of demos. Let me skip ahead. That's a interesting model. I'm going to skip ahead to this VJEPA model. So this is a model that's trained for video. It's not trained to predict in time. It's trained to predict missing parts in a video. So you take a video, you corrupt it by masking some parts of it, and then you run them, the full video and the corrupted one, through encoders, and simultaneously you train an encoder and the predictor to minimize prediction error. And in the end, you get a very good representation of short video clips of 64 frames or something like this. It gives you a really good performance when you train ahead on top of it to classify actions. And what's more interesting is that this system has learned some notion of intuitive physics. So if you show it a video like the one at the top, where a ball was thrown and is kind of flying through the air, and then all of a sudden it disappears, the prediction error shoots to the roof. Okay, because the system tells you like that's not possible. Like, I did not predict this. And so it detects the deviation from the prediction, which means it has integrated some notion of intuitive physics. And, there is a validation of its internal model here. And it's the first time I've seen any model that has this type of intuitive understanding of reality. We have various tests for that. And there's a new version of it that we can use for planning, and I'm just going to show you a video that system can, you give it a target position for a robot arm. It's never really seen this robot before, and it can actually plan a sequence of actions to by optimization to move the robot towards the target position, which may include grabbing an object and kind of moving it. So this is a simple planning problem, but the point is that there's never been any training for that particular task. You give it a goal, and it figures out the sequence of actions to satisfy this goal. Okay, so let me not bore you with details. There is ultimately what we're working on right now is a technique that to train those JEPA, we use a technique that consists in sort of estimating the amount of information that comes out of the encoders, and we try to maximize that information. So when the system learns, it tries to find a trade-off between maximizing the information content coming out of the encoder, but yet only keeping information that it can predict so as to minimize the prediction error. Okay, so it finds this trade-off. Let me actually skip ahead to the latest way to do this. This is a method that is a few years old and worked well. But we have this new thing that's called SIGREG, and that means sketch isotropic Gaussian regularization. And the whole system is called JEPA. I'm not responsible for the name and for some of the paper, but let's say you have data that comes to you in a space, ambient space, and within some manifold, but you have zones of high data densities, and it's kind of wrapped up in something complicated. You feed this to a neural net, and you put this into some representation space. You like this representation space to have some interesting property. And one property that we insist it should have is that it should be an isotropic Gaussian. It basically should fill up the space. If it fills up the space with an isotropic Gaussian, it means that there is as much information as you can extract from the input in that representation. So the way you do this is that you take all your data points, there may be multiple data points in each of those blobs, you project it along multiple dimensions, and the way to characterize an isotropic joint Gaussian distribution is that every marginal distribution along any projection is a Gaussian with the same variance. Okay? So you make multiple projections, and then you measure the invariable distribution. In fact, what you can measure is the cumulative distribution. And then you have some cost function that measures the discrepancy between the Gaussian and that distribution, and you move all the points so that that thing becomes Gaussian. And it works amazingly well. So I'm going to skip ahead and give you two conclusion slides. So abandon generative models in favor of joint-embedding architecture. Abandon probabilistic models in favor of those energy-full models. Abandon contrastive methods in favor of those regularized methods. Abandon reinforcement learning. I've been saying this for 15 years. And if you are interested in Controllable AI, you should not work on LLMs. You should work on those JEPAs or those wild models, which is basically what I'm doing. And really, the key idea behind those JEPA is this idea that you need to learn abstract representations. And the way to train hierarchical JEPAs is that the high-level JEPAs that predict at the level of high level of abstractions are trained to predict long-term. If you want them to predict long-term, they have to eliminate a lot of details about the state of the world, otherwise they're not going to be able to make that prediction. So that's how you would build hierarchical models. And I thank you very much. And this,
we have time for questions.
You mentioned the guardrails. We know that every big system has bugs in it. Can we have guardrails that can be guaranteed to resist any bugs in the guardrail or bugs that result from the running of the system?
No. Short answer. Okay, it's like this. We have guardrails, in the world for humans. They're called laws. Okay, we have hardwired guardrails in our brain that basically inhibit certain behavior that most people who are not sociopaths will not do. Okay, they are built into us by evolution so that we don't kill each other all the time, although it fails most of the time. But we also have guardrails that we build ourselves that which is the way we build our societies, and they're called laws. And no one can guarantee that the set of laws that is enforced today in any particular country will prevent any bad things from happening. It's just impossible, right? So we're gonna have to live with this. It's like, guaranteeing the safety of an AI system is sort of like guaranteeing the safety of a turbojet engine. You can just do your best to make turbojet engines as reliable as possible, and they're amazingly reliable, like they should not work, right? I mean, any turbojet engine should blow up in a few minutes, given the forces and temperature that they're submitted to. Yet you can fly in complete safety halfway around the world on a two-engine airplane. That's amazing to me. So it's going to be the same for AI. We're going to have to figure out how to make them safe, like iteratively, by adding guardrails to them. But we're not going to have a magic bullet. Already proof.
So, in the robot example, the robot's poise is determined by a set of numbers that presumably encode the angles at each joint. Is that the abstract representation from the image?
No, it's much higher abstraction, right? I mean, the system looks at the image. So we have different versions of this. There is one where it knows it has like numbers that indicate the position of the joints. This is a version where the only thing it sees is just a video.
But if it's going to control the robot, it has to know that there's a button to push somewhere.
Yeah, no, it knows what actions to take, okay? And there are several ways to control a robot. You can send torques, or you can send, desired XYZ position of the end effector, which is the case here. I mean, there's all kinds of ways you can specify that. So it knows that, right? It knows the set of actions, like the vector of controlled variables.
The actions A.
Huh?
Those the actions
The
A?
action A.
Okay.
Yeah.
But by construction, they don't know the interpretation of their representation.
Right,
That's right.
Yeah, that's fine.
FNO.
Oh, so my question was about your sort of grand plan. It seems to me that there's a fundamental aspect of the way we work that is still not present, which is the fact that we learn continuously. And when I make a mistake, it physically hurts to make it. Like I send a report with I submit a grant with a mislabeled figure. I don't sleep for a week.
Right.
Like I actually physically hurts every other sense.
I feel
so where is that? Right?
It is there. It is there.
The negative reinforcement.
I didn't actually kind of dwell on this, but it is there. Let me show you the relevant slide. Okay, so yes, remember I showed you this diagram, right?
Yeah.
So this is immediate pain. Okay, so if you take an action, so let's imagine this is not planning, but it's you actually take an action in the world. There is through your perception module, there's something that is going to cause immediate pain. Like if I approach you and I pinch your arm, okay, it's going to hurt. That's immediate pain. That's hardwired into your brain as a cost function. That indicates that you want to avoid this.
But you still have to stage the prediction and the learn, right? It's not
happening
continuously.
So now, once I've pinched you once, the second time I approach you, you're going to recoil or do something to prevent me from pinching you. And that's because of your one model. Your one model now was adapted and sort of has a picture, a model of me as a pincher, and so you predict that the outcome is not going to be good, and you plan actions to prevent this outcome from from happening. Emotions are basically either
But
immediate.
to use that example,
Yes.
if I didn't know you and you approached me,
Right.
I would imagine that it's gonna be bad, right? So I would actually recall before you actually touch me. So in some
Only
way,
if I look mean, you know?
But that might, if I was to ask a question, it would be an extension of this, which is you opened by saying that real intelligent systems have very strong motivations.
Yeah.
And motivation, this is a very weak sense of motivation. You know, like this cost function is a very weak sense of motivation. Like our motivations have all sorts of kind of very long-term and very distant things that and are transcend all sorts of minor questions. Like we're willing to take lots of short-term pain
Yeah.
to meet long-term goals and
That's
so on.
right.
Like motivation feels like a very solved problem.
so what's human's objective function?
Well, we have a whole bunch of them, which are hardwired into us by evolution, but they're not particularly kind of long-term. We certainly have a motivation to not die. We have a motivation to reproduce, most of us, not everybody.
10-year track is definitely long term.
Right? But that's a sub-goal to kind of a longer-term goal, right? Which is probably societal recognition, certainly not money, that's for sure.
For sure.
But let me take an example. Like, you know, nature tells us that we're hungry, and that's an immediate emotion. It doesn't tell us how to feed. We have to figure this out. Like how to satisfy this objective is not something that nature tells us how to do. We have to use a one model and figure out what actions will satisfy this drive, right? And it's similar for other things, like certainly reproduction.
I think we should thank Yann again. Before we do, let me just say that we'll go down the hall and down to the 8th floor where there's wine and snacks, and we've got an hour, so there's plenty of time to mob Yann. But we are going to get him to wine. That's a high priority thing. Let's thank Yann again.
Thank you.